Sputtering is a process whereby particles are ejected from a solid target material due to bombardment of the target by energetic particles. It only happens when the kinetic energy of the incoming particles is much higher than conventional thermal energies. This process can lead, during prolonged ion or plasma bombardment of a material, to significant erosion of materials, and can thus be harmful. On the other hand, it is commonly utilized for thin film deposition, etching and analytical techniques. Physics of sputtering. Physical sputtering is driven by momentum exchange between the ions and atoms in the materials, due to collisions. The incident ions set off collision cascades in the target. When such cascades recoil and reach the target surface with an energy greater than the surface binding energy, an atom would be ejected, known as sputtering. If the target is thin on an atomic scale, the collision cascade can reach the backside of the target and atoms can escape the surface binding energy. In transmission, the average number of atoms ejected from the target per incident ion is called the sputter yield and depends on the ion incident angle, the energy of the ion, the masses of the ion and target atoms, and the surface binding energy of atoms in the target. For a crystalline target, the orientation of the crystal axis with respect to the target surface is relevant. The primary particles for the sputtering process can be supplied in a number of ways, for example by a plasma, an ion source, an accelerator, or by a radioactive material emitting alpha particles. A model for describing sputtering in the cascade regime for amorphous flat targets is Thomson's analytical model, an algorithm that simulates sputtering based on a quantum mechanical treatment including electron stripping at high energy as implemented in the program TRIM. A different mechanism of physical sputtering is heat spike sputtering. This may occur when the solid is dense enough, and then the incoming ion heavy enough, that the collisions occur very close to each other. Then the binary collision approximation is no longer valid, but rather the collisional process should be understood as a many-body process. The dense collisions induce a heat spike, which essentially melts the crystal locally. If the molten zone is close enough to a surface, large numbers of atoms may sputter due to flow of liquid to the surface or micro-explosions. Heat spike sputtering is most important for heavy ions with energies in the keV-MeV range bombarding dense but soft metals with a low melting point. The heat spike sputtering often increases non-linearly with energy, and can for small cluster ions lead to dramatic sputtering yields per cluster of the order of 10,000. For animations of such a process, see displacement cascade 1 in external links. Physical sputtering has a well-defined minimum energy threshold equal to or larger than the ion energy at which the maximum energy transfer of the ion to a sample atom equals the binding energy of a surface atom. This threshold typically is somewhere in the range 10 to 100 electron volts. Preferential sputtering can occur at the start when a multi-component solid target is bombarded and there is no solid-state diffusion. If the energy transfer is more efficient to one of the target components, or it is less strongly bound to the solid, it will sputter more efficiently than the other. If in an alloy, the component A is sputtered preferentially, the surface of the solid will, during prolonged bombardment, become enriched in the B component, thereby increasing the probability that B is sputtered such that the composition of the sputtered material will be AB. Electronic sputtering. The term electronic sputtering can mean either sputtering induced by energetic electrons, or sputtering due to very high energy or highly charged heavy ions that lose energy to the solid mostly by electronic stopping power, where the electronic excitations cause sputtering. Electronic sputtering produces high sputtering yields from insulators, as the electronic excitations that cause sputtering are not immediately quenched, as they would be in a conductor. One example of this is Jupiter's ice-covered moon Europa, where a MeV sulfur ion from Jupiter's magnetosphere can eject up to 10,000 H2O molecules. Potential sputtering. In the case of multiply charged projectile ions, a particular form of electronic sputtering can take place that has been termed potential sputtering. In these cases, the potential energy stored in multiply charged ions is liberated when the ions recombine during impact on a solid surface. This sputtering process is characterized by a strong dependence of the observed sputtering yield on the charge state of the impinging ion and can already take place at ion impact energies well below the physical sputtering threshold. Potential sputtering has only been observed for certain target species and requires a minimum potential energy. Etching and chemical sputtering. Removing atoms by sputtering with an inert gas is called ion milling, or ion etching. Sputtering can also play a role in reactive ion etching, a plasma process carried out with chemically active ions and radicals, for which the sputtering yield may be enhanced significantly compared to pure physical sputtering. Reactive ions are frequently used in secondary ion mass spectrometry equipment to enhance the sputter rates. The mechanisms causing the sputtering enhancement are not always well understood, but for instance the case of fluorine etching of C has been modeled well theoretically. Sputtering observed to occur below the threshold energy of physical sputtering is also often called chemical sputtering. The mechanisms behind such sputtering are not always well understood, and may be hard to distinguish from chemical etching. At elevated temperatures, chemical sputtering of carbon can be understood to be due to the incoming ions weakening bonds in the sample, which then desorb by thermal activation. The hydrogen-induced sputtering of carbon-based materials observed at low temperatures has been explained by H ions entering between C-C bonds and thus breaking them, a mechanism dubbed swift chemical sputtering. Applications and phenomena. Film deposition. Sputter deposition is a method of depositing thin films by sputtering that involves eroding material from a target source onto a substrate, e.g., a silicon wafer. Resputtering, in contrast, involves re-emission of the deposited material, e.g., CO2 during the deposition, also by ion bombardment. Sputtered atoms ejected into the gas phase are not in their thermodynamic equilibrium state, and tend to deposit on all surfaces in the vacuum chamber. A substrate placed in the chamber will be coated with a thin film. Sputtering usually uses an argon plasma. Etching. In the semiconductor industry, sputtering is used to etch the target. Sputter etching is chosen in cases where a high degree of etching anisotropy is needed and selectivity is not a concern. One major drawback of this technique is wafer damage. For analysis, another application of sputtering is to etch away the target material. One such example occurs in secondary ion mass spectrometry, where the target sample is sputtered at a constant rate. As the target is sputtered, the concentration and identity of sputtered atoms are measured using mass spectrometry. In this way, the composition of the target material can be determined and even extremely low concentrations of impurities detected. Furthermore, because the sputtering continually etches deeper into the sample, concentration profiles as a function of depth can be measured. In space, sputtering is one of the forms of space weathering, a process that changes the physical and chemical properties of airless bodies, such as asteroids and the Moon. On icy moons, especially Europa, sputtering of photolysed water from the surface leads to net loss of hydrogen and accumulation of oxygen-rich materials that may be important for life. Sputtering is also one of the possible ways that Mars has lost most of its atmosphere and that Mercury continually replenishes its tenuous, surface-bounded exosphere.